All right, let's get started. Welcome everybody to yet another C++ session at Build. How do you feel? I'm sorry, I'm hard of hearing. How do you feel? Thank you very much. And I know we've had a lot of C++ talk. In fact, before the camera went on, sorry for those of you at home, we were chatting a little with the audience as everyone was coming in. And we had questions like, what's the talk about? And how many people here are under the age of X and such? And yes, there are a lot under the age of 30. But one of the interesting things I happened to say in passing was, I'm sorry, there's only one WinRT slide in this talk, and there was cheering. So, no, not again. Because WinRT is great and beautiful. But the key point is that C++ is about a lot more than WinRT. It's about cross-platform, cross-compiler, cross-operating systems. And that's the part of C++ we're going to be talking about here. So in particular, as we talk about writing modern C++ code, this is still very much about Microsoft and about Microsoft technologies. And we care deeply about making sure C++ stays relevant in our platform. And that includes on important game-changing devices like tablets and systems like WinRT. It includes on anything performance critical where access to the hardware, which is C++'s bread and butter, is still, make sure that's still available. That's like C++ AMP, which we're also doing in this release, which we've had talks about. And it also means, as another pillar, conforming ISO C++. So we're very happy in this release that we've now completed the full C++ 11 standard library. That standard just shipped a month ago. Geneva has almost published it. And in Dev 11, you are going to get a fully conforming C++ 11 C++ standard library, which is really nice. Now, having said that, so we're happy about that. Threads, atomics, futures. And by the way, those futures, it's not just like, we implemented threads. We implemented lot mutex and the standard std : way. We also did things like extend our proprietary libraries like PPL, which Intel has implemented that, our parallel patterns library. So you can use that on Linux today if you didn't know. We've make that available for other people to implement. So if you like PPL and you haven't been using it because you can't use it on Linux, well, that's not a reason. But as we do that, we've also improved PPL and integrated that with STD futures. So it's not just here's a feature in the standard and here's the Microsoft libraries. No, that's the way things are supposed to play together. And so we've really taken care not to just check off features, but do this. Let me just say, though, that we do not implement all of the C++ 11 language features. Now, the standard is just new, but still, people are proactively expecting us to implement the standard, and we did. And the compiler you already have had in your hands for a year or two was the first in the world, or among the first, to implement move semantics, R-value references, including throughout the STL, decal type, auto, lambda functions, which are such a game changer. And in fact, our experience there drove the standard and the syntax. But it's true that in this release, we haven't done more. So let me just mention up front, because some people wonder, why didn't we? Did we think WinRT was so important? Yes, we did, because if C++ isn't relevant, it's not going to get invested in. And this is a game-changing thing across the entire industry, not just one company. So that's why we've invested in WinRT heavily. We've also invested in GPGPU with C++ AMP, because it's incredibly important for C++ to be the language of performance. If there is a language lower than C++, that it has more performance, we didn't do our job as a C++ community. And I mean that broadly in the industry, not just Microsoft. And so we invested in C++ AMP. We're implementing it, and so are several now of our partners implementing it in their compilers for Windows and non-Windows platforms. So we really think it's important, and we're very glad to be seeing that we're helping drive the industry and not just doing it on our own. But doing WinRT and doing GPGPU we felt was critical, was Pri 1 to keep C++ relevant in this very importantly changing world in these two areas. But I'm not going to say next, therefore we didn't do any C++ 11 language work, because we did that too. The only trouble was we got caught in a trap. We picked variadic templates. And it turns out they're not as hard as export, but they're about 2 or 3x harder than we thought they would be. So we've got them almost done, but they didn't fit into this release. We've invested in, and nobody is more disappointed than our community and us and the developer who spent midnight oil on it. So the bad news is that we've only done minimal new C++11 language features, ISO standard language features in this release. But the good news is we've done the entire standard library that is now available, including workarounds for where language features like variadics are missing. And we've got a nice shelf set just ready to drop into a future release after VC11, VS11, with variadics templates almost done. But it's not going to be in VC11, it's going to be post VC11, and the only thing I will add to that is do not assume that post VS11 is a code for 2 or 3 years after VS11. It is not a code for that, but we'll see what we can do. But they're almost done, so we are disappointed too. We wish we could have done more. Having said that, we've already got a lot in the existing product, and now you've got the complete C++ standard library, including many of the things we are now going to talk about. So let me frame up this talk. This talk is to show that writing code in C++ is clean and safe and fast. It is clean. You can express with minimal lines of code and boilerplate what you want to do, just like in all the other modern languages, C#, JavaScript. It is safe, meaning that code that you write in the clean way is exception safe. It's not fragile. You don't have to deal with error codes and all of those things that make code nice and safe and type safe. And memory safe, so you don't have to deal with memory deallocation. It's also fast because this is C++. So now that's my claim, that modern C++ is those three things. That was not true a dozen years ago. So what's changed? That's why we're here. So if you have done C++ before, how many of you have done C++, say, more than 5 years ago? Oh, OK, quite a few. How many of you know that C++ code is fast, but it's just harder to write than in other languages? And I heard about half of you, and I've heard some grumbling. So that completely used to be true. Did you hear about the ALM support for C++? C++ CLI, IntelliSense, all of the cool stuff that we're doing in this release. So we're doing a lot of good work for C++ that shows that it's tool-friendly, including XAML and other tools that now are available also for C++ first. But let's talk about how even portable, standards-conforming, native ISO C++ code, modern C++ code, really is safe and clean and fast. So the motivation I'll talk about, then I'll talk about why modern C++ can be viewed this way. And then just a couple of slides at the end talk about what do you do when you want to go outside of C++ across module boundaries to talk to other languages, or even to C++ code not compiled with your same compiler. So first, the motivation. There is this great shift in the industry where native code is having a renaissance. C++ code is having a renaissance. And the main reason is because performance per dollar is king again. It has been king for the whole history of computing except the last 10, 15 years. And that is now swinging back. Because for 10, 15 years, we had all this excess power because computers kept getting power and we weren't doing anything significant with them. We shipped WIMP interfaces, windows, pointers, mice, all those kinds of things. And the menus, the icons, and we called it good as an industry by and large for 15 years. And now we have demanding applications. We have Kinect and sensors. We have all sorts of cool stuff, Metro applications. And that's putting more pressure on doing more, bigger experience, but we're also going mobile with less hardware. We're going to the data center, where you might think, oh, but that's lots of hardware. Yes, but 88% of data center costs come from power, distribution, and consumption, and from servers. And if you can run on half the machines, you can have 88% of your data center costs. That's a direct 44% savings on typical data centers. So safe code matters, and fast code matters, and that efficiency is worth optimizing for more and more. And so because of this, we've already been seeing at Microsoft, within Microsoft developers, but also across the industry, more and more people coming back to C++. And sometimes they feel apologetic. It's like, well, I did C++ because it was faster. I know, but call me a masochist. And this whole talk is about, and you don't have to add the words, but I might be a masochist at the end, because it's just as clean, and here's how. So I'm going to assume you know how to program. We're at a developers conference after all, but we have a lot of people on the web, so thank you for tuning in also. And I'm going to assume that you're a software developer, have some idea of software development, not necessarily with C++ though. I am going to assume you know how to program, but if you have known C++, I may point out to a few things that have changed that we may need to unlearn, because that's the old way we did things that doesn't apply anymore. And the whole point is how elegant it is to write clean and safe and fast code in C++ today. The first thing before I get into code is just the mindset. Here is how you should think in C++. You should think that where C came along in around 1970, and it for the first time gave us a portable language that was efficient and close to the hardware and portable. Bjarne came along 10 years later with C++ and said, and you can get all that efficiency and portability plus strong abstraction. That is what you want. That is what you get from C++. You want strong abstraction, type-safe object code, type-safe generic code. You have great modeling power, specialized templates, all sorts of things, and whatever you want to say, you can say it without sacrificing control and efficiency. You want full control over your code and memory. In particular, you control exactly where memory goes, exactly what layout is, and that's very important for multi-core machines because you have things like false sharing and ping pong. You have two things on a cache line. You have, that's bad. You want to be able to prevent that. You also want, however, to prevent pointer chasing data structures in memory where performance is important and deal in arrays. Some languages make that very, very hard to do where you have to fight the language to get that done. But that efficiency is the default in C++, and you still have full control over exactly how your memory, how your data is laid out. But at the same time, you get pay-as-you-go efficiency. You always can open the hatch and do it yourself if you need to, or tune it. But if you close the hatch, things are clean and easy. They really are. And let me try to show that. And you don't pay for something unless you use it. And here's a nice quote from my friend Andrei Alexandrescu, who's been working at Facebook for the last year or so as a research scientist. And Andrei has come to know a little bit about medium-sized data sets. Here's a quote from him that I think resonates as you see how Google is heavily invested in C++, how Microsoft has also always been heavily invested in C++ for their code, how now Facebook is built on C++. The going word at Facebook is that reasonably written C++ code just runs fast. That's because you don't pay for things that you don't use, which underscores the enormous effort, and he's speaking from some personal and friends' experience here, the effort spent at optimizing PHP and Java code. Paradoxically, C++ code, I'll paraphrase, maybe, because I don't actually think this is necessarily true, but maybe more difficult to write than in other languages, but efficient code is a lot easier to write in C++ than in other languages. Do you agree? So I heard the applause starting, and see, so you guys get it. But I wanted the people who are watching this to hear you because they may be Java developers. They may have heard that, oh, C++ is this performance Nazi thing. No, we're inclusive. This is not a rant against Java. Java is fine for what it is. C# is a great managed language from Microsoft that is probably the premier managed language in the entire world. And that's when you're optimizing for programmer productivity. When you optimize for performance, control, efficiency, that's C++'s game, and they're complementary. You can and should use both together. Oh, and by the way, why not HTML, XAML, and JavaScript at the same time? It's all good. And this is what this conference has been about. So let me now go and talk about this modern C++ and how it looks. Now, if you've seen C++ before, then the left-hand side of this screen is going to look kind of familiar. So I have a new circle. I make a vector of shaped stars. Shape is some abstract interface. And then I go through this for loop, and I go through and I check for each shape if the pointer isn't null, and I check to see if it's a match. I use the overloaded equality comparison operator. Oh, and then I go through and I delete all the shapes in the vector because the vector doesn't own the pointers in the vector, otherwise I'd leak. And then I delete the new circle that I created. And let's assume that this code isn't all in the same function, and so therefore, because the code isn't all in the same function, I may need to do this new and delete. But even if it is in the same function, that's the C-ish way, the C with classes kind of way. We're still using STL and such, but there's a lot of manual management done here. By the way, one more thing. I'll say one more thing about the code on the left. it's incomplete. It's longer than the code on the right, but it's actually not complete, and I'll point out why. The way you write the exact same code naturally, and I want this to flow out of your fingers. All of the code I'm going to show you works in Visual Studio. And so Visual C++ allows you to do this, the standard conforming ISO C++ code, except for the last slide on WinRT. You should use auto, which simply reduces the type. Why should you say it again? Some people have been nervous about that, but it's syntactic sugar for just compiler, cough up the type. Beat you over the head until you cough up the type because you know what it is. If you just said blah p equals something, the compiler can tell you, by the way, instead of blah, you should have typed exactly this. And you say, well, why didn't you just write it for me? We hate that when the compiler gives an error message saying, I know this is exactly what you should have written. Now you go write it. So 1990s. Anyway, so auto is like C# var. And that's what we want in the type deduction in other languages. It's a small feature, but it's really convenient, so use it. Instead of new, notice we use make shared. So I talked about auto for type deduction. Instead of new, prefer by default to use make shared as your allocator. I'm going to talk about another option for unique pointers, but by default, if you really want to heap allocate something, use a reference counted smart pointer. Now, most of you already know that. How many of you already use reference counted smart pointers for some or all of the objects in your code? Great. Now there's a standard one. So you don't have to use a different one in every project, on every library interface of a library that uses their own as you link it in. There's one, shared pointer. Let's use it. I now have a vector of pointers, but they're a vector of shared pointers. And therefore, I have to clean up the vector? No. So by simply saying vector of shared pointer, I am declaring my intent that this vector owns the pointer to objects, even though I'm using an indirection, and that's just fine, which means I have no need for a delete of anything. I don't need to delete that circle. I don't need to delete all those shapes I loaded into the vector. I get automatic lifetime management. I probably never need to write delete ever again. And this code, by the way, is exception safe, which the code on the left was not, because if an exception ever occurred, you would leak everything, despite your heroic efforts to manually clean up everything on the left-hand side. So the code on the left-hand side is actually roughly twice as long, possibly worse, depending on how many control flow paths you have. As Scott Myers would like to say at this point, have a nice day. But the good news is we can have a nice day because modern C++ code, none of that is true. And so if you're thinking of C++ as automatic memory management, not exception safe by default, exception safety is hard, oh, I have such good news for you. It's not like that anymore. We woke up. That was just a dream. It'll fade. And we're now in the real world, just like every other modern language. Clean, simple, safe code. By the way, you might have noticed that instead of a for loop, a naked for loop, I happen to use an STL algorithm. Did you notice I used a lambda function? I simply said iterate from begin of EW to end of EW with this lambda. And that syntax is only going to get better, but it's already very convenient. And that simply says, here's my loop body as a function object that I can write on the fly, just like Java function or C# anonymous delegates and lambda functions. So that makes it very convenient. In fact, every STL algorithm and every new loop, every new function you write that takes iterators is almost as good as a new built-in loop in the language. That's really powerful. You want to extend the language? Here's your chance. And it makes STL enormously more usable. In fact, one reason I like to talk about this, and we'll talk about for each later, but I'll hammer on it here. On the left-hand code, if you're parsing through the code, you're a compiler or a person reading through the code, and you get to the word for. See it there in the middle? For, vector, blah, blah, blah. But when you stop at for, I don't want you to go any further. I don't even want you to parse the next token, the paren. When you see for, what do you know? It's a loop, okay, and? Crickets. Nothing. It's a loop. Okay, now what next? Now, I know that because you're a human being, as you look at the for, your eye, just in your peripheral vision, is scanning to the right and saying, oh, but I see equals begin, and I see something about it doesn't equal, and I see something about end, and I see plus plus. I know what that does. Yeah, and how many of you have guessed wrong about that? Your peripheral vision has let you down because it didn't actually say that, or because the loop control variable was modified in the body of the function. For tells you only a loop's coming. Go parse it to figure out what it actually does. On the right-hand side, as soon as you see for each, before you even look at the open bracket, what do you know? It's a loop, it's an iteration, it's going to touch each element exactly once, and in what order. I haven't even looked any further yet. You really are at a higher level of abstraction. And all these STL algorithms, which have been in the standard for 15 years now, because of lambda functions, have just got 10 to 100x more usable. And I don't think that's an exaggeration at all. Because Scott Myers and others have long said in Effective STL and other books, prefer algorithm calls to hand-coded loops. It's just that they were too hard. So it was good advice, but it was too inconvenient to follow. And now it is convenient, and so that's modern C++ code. So let me continue by showing some of the other features that we can look at in the standard. The first thing is, by default, don't even think about deleting things. If you have shared pointers and unique pointers that own the things they point to, you never need to write delete again. I'm curious because this is actually something where when people talk about modern C++, I've blogged about it and I've given talks about it, and in the blog comments people say, oh, but C++ is still so hard, you have to delete. And there's usually people who say, I haven't written delete in years. How many of you have not written delete in years in C++? So you get it already. More and more will get it. That is old school. So here are some things that have never changed that C++ has always had. So this is not new. This has always been there. C++ is great at automatic lifetime management. And automatic, on the right-hand side of the screen, means automatic storage duration. That's our word for stack-based or scope-based variables, which are great because they're nested. They're automatically destroyed, exception safely at end of scope, all that good stuff, which other languages like C# has invented using the using block to express the same thing, because it's important. Java now in Java 7 has finally added the try with resources statement, which is the same thing. So they now have it too. They've reinvented the scoped storage duration. It's just the natural way you create objects in C++. This is what you should just naturally write, unless there's a reason to put it somewhere else, like on the heap. Look, I want a widget. There it is. And I say dot draw, just with direct syntax like any modern language. But on the left-hand side, you'll notice you also can express something important in C++, and that is my gadget is a directly held member. There's no pointer there. There's no indirection. It's a directly held member, semantically, of this enclosing class. Now, in native C++, you're guaranteed that gadget is actually in line inside the class, so it affects the size of the enclosing class. It's really inside there, and its lifetime is tied. That's actually kind of an implementation detail. In WinRT now, as I mentioned in my talk yesterday, you can have a ref class inside another ref class held by value. And those are actually two heap objects, and the one has a pointer to the other, but you don't see that. You just say in your code, you just say ref class instead of class. Exactly the same thing works, and we destroy them. We wire up the destructors, and everything happens exactly with normal semantics. Now, the nice thing about this is, because gadget's lifetime is automatically tied to the enclosing object, I don't ever need to say anything about its lifetime explicitly anywhere in the program. This is just plain old C++. Yes, I have to manage the lifetime of maybe the widget object, but whatever I did for it is naturally flows to the gadget object. There can never be a leak. If I control the widget's lifetime and clean it up, there can never be a leak of a gadget. This is naturally exception safe, and I wrote zero code to get there. It's just the default, safe and convenient by default. With the widget on the stack, the lifetime is automatically tied to the enclosing scope. I can't get it wrong. I can't accidentally forget to delete the object because it's as if a finally block was written at the end for me. And that's just the default in C++. Yes, you can escape a pointer to it if you try. We protect against Murphy, not Machiavelli. If you have leanings toward that of the 15th century count, well then, he can still go and get his dagger and do damage. But the default is clean, safe, fast. And you get that automatic destruction and deallocation not just for the widget object, but notice the caller has no idea there's a gadget inside the widget, and he destroys the gadget too. And it just is naturally working. Now, what if you need to reach for heap lifetime? Because sometimes automatic lifetime attached to a scope or as a member of another object isn't going to do it. So then you have it can also use shared pointer, where I have widget has a shared pointer to gadget, which means that even though I'm holding it by pointer, his lifetime is still attached to mine. Because there may be times you want to hold it by pointer. For instance, you may have an incomplete or opaque object or something, or some other reason why you want it to be on the heap. You're holding a pointer to base, and you don't know what derived thing it's going to be. That's perfectly fine. It means you can't lay it out in line, but you can still attach the lifetimes, and that way you control the lifetime of the widget. The gadget just comes along. You never need to manage the lifetime of it explicitly. Certainly never delete it. Now, what if you've got a reference? So even though the shared pointer shows the shared ownership, it keeps the gadget alive, so there's no leak, it's exception safe. The weak pointer lets the gadget also refer back to the widget if it wants to. Now, if that were a strong shared pointer that keeps it alive, that would be a reference count cycle, and it would never be freed, never be deleted, right? Because reference counting doesn't clean up cycles. Is that, a big problem with reference counting? Well, no. It's very rare that one object really owns another object, and that object owns you. Those things can't both be true. It is very rare to actually come up against an example in reality where that's not just a bad design. So in other languages, like in Java, what you actually do here is you have to say widget has a gadget, and when widget disposes or closes, I have to remember to manually wire up the dispose to call the gadget dispose, but not to do the same thing for the gadget which has a widget, but his dispose, I have to remember he doesn't call. It's the same issue, it's just more convenient here. And I just say declaratively, widget owns the gadget, that's what shared pointer means, and gadget doesn't own its widget, but it refers to it. But it's safe because weak pointers can test whether they dangle. So if you used a raw pointer here, it would be type unsafe. This is perfectly type safe. Nothing can go wrong if you stay within the system. By the way, I would have used unique pointer here, but I used shared pointer for a reason. Because imagine that widget owns its gadget, but it might share ownership with other things. You might expose it. You might get or borrow a gadget from somebody else produced and be one of many people using it. Then you have a shared pointer. If, however, it's a unique implementation detail, then you use unique pointer. For example, if you have a node in a tree, and the tree, each node has several children. So it might have a vector of node pointers. The way we spell that is a unique pointer because I'm the only pointer there's ever going to be to that other thing. I own it uniquely. The reason you use the unique pointer is it's more efficient, doesn't need a reference count, and it's extremely fast. And raw pointers are still okay. Notice there's a node star to the parent. So let's take a look at this. So the children, vector of unique pointer says that I own each child uniquely. I'm the only one who owns it. It just happens to be, for whatever reason, I have a pointer to base or whatever, it's in a direction. Node star parent may make you think, oh, unsafe, C pointer. No, it doesn't own it. Distinguish between pointers that own things, raw pointers that own things, those are unsafe, you have to remember to delete, versus raw pointers that observe things whose lifetime is guaranteed to outlive them by construction, like this case. We're guaranteed by construction of the program that the parent will outlive the children, so the child can have a raw pointer to its parents all it likes. And if for some reason it's not true by construction, then you can use something like a unique pointer instead. But in this case, it's perfectly fine to have a raw pointer in this system, in this type-safe C++ world, and have no issue, still have automatic memory management, no need for garbage collection or any other thing. And the raw pointer just observes something. It doesn't own it, it just observes it, something that's going to outlive it anyway. And notice this is the one place where you might still write plain new, is to initialize a unique pointer. So there is no make unique like make shared in the standard. for various technical reasons, and it just wasn't proposed, so there isn't one. So you still say new in portable ISO C++ code, because that's what the standard says, but immediately you convert it to a unique pointer, and Bob's your uncle. And you're converting it to something that owns it, so as soon as you finish that construction, no matter what else happens, you're guaranteed it's going to get cleaned up. How many of you say, yeah, but I would still love to use a raw pointer and delete somewhere? Come on. Oh, phew. At least not willing to come out of the closet just yet, so that's all right, because I just had said all this bad stuff. Okay, occasionally, if you are one of those people who is implementing the stuff that people get at under the hood, so it's not just you're under the hood, it's that you're actually down inside implementing the engine or the carburetor, you're implementing your own data structure, I can do better than reference counting, fine. Inside your type, whether it's a vector or a node or whatever, go nuts and use raw pointers if you want to be careful and you want that extra efficiency. We're here to get out of your way whenever you want it. It's just that's not the default. Just open the hood and use that feature if you need it, but make it well encapsulated so it never leaks out to the rest of the system. So tactically, you can squeeze that last bit of performance if you need it. But by default, you've got a fast way that's nearly always just as fast, and the measure of performance difference is not measurable, and you're nice and safe and clean. By the way, all the code we've seen is clean and nice, just like any other modern language, and safe by default, and more efficient by construction. What's not to like? Bjarne has a point. It doesn't need elaborating. If I were to elaborate, if you express your object lifetimes by construction, this object owns another because it's a member, or this scope owns the object because it just lives in it, or this smart pointer owns this object, you're done. There's nothing more to say because, oh, but what about the smart pointers? Well, they're owned by objects or they're in a scope. You're done. There's no garbage to collect. So what about containers? In the standard, we have the little v vector container. So if I have a vector of standard strings, I can push back getEli, and that's the default container you should reach for. So every so often somebody says, well, what's the default container I should use in C++? And unfortunately, and sorry, Scott, but I don't agree, and you know I don't. In effective STL, perhaps the only item I disagree with is the one where for a paragraph it says, well, there is no default container. You should use the right one, know all the details of which the right one is for your job. And that latter part is still true. But there sure as anything is a default container. It's called vector, just use it. It's the array that resizes itself. It's heap-based, but it always owns the contents. It's always exception safe. It's always efficient with 0 per element overhead. It's compact. It's the most efficient and cache-friendly for navigation if you're traversing the whole thing. There is nothing not to like about it. Use it. Now, okay, that's the default. But by default doesn't mean only. So it's the default. If you don't have another reason to use another container, use a vector. It's always been there for that. By the way, you will find Bjarne says exactly those words in the C++ programming language because that's how the design is. If, however, you need to have, you have a vector whose size is fixed and will never change, like a C array would be, a safer way to express it than reaching for a C array is to have a standard array. This is new in the C++11 standard. It was part of TR1, the technical report on library extensions, and is now normative, and it's in the product, has been since our last release. Array of string, comma, 50 in this case says there are 50 items, never more, never less. You cannot insert, you cannot push back, but you can access all those items. And unlike a C array, it's perfectly safe to use and plays nice with all of STL algorithms. So reach for that when you already know there's a fixed size buffer, and I'm going to make sure I know by construction somehow I'm not going to overrun it, and this is the right size for it, or overlay something else. You can use array as a fixed size vector and avoid heap allocation at all. You can get rid of all allocation overhead. That's the control with C++. Now, the other major kind of container you may want is an associative container, a key value lookup container. And the usual example is phone book. So your default container there should be a map or a multi-map. Multi-map just means you can have more than one of the same key in it. So if a person only ever has one phone number, use a map, but oh, Neil Peart, he can have 2 phone numbers. So home and cell. Nobody uses home anymore, right? There's only cell. That's the only phone number. And your work forwards to your cell, right? So there's really just your, oh, never mind. Yeah, I just don't call otherwise. Anyway, so map and multi-map are your default ones. And if you want hash-based containers, because map and multi-map are tree-based, use the unordered underscore versions of them now also in the standard, and they give you control, they give you different performance characteristics. So it's hard to say, oh, map should be your default or unordered map should be your default, because map is easier to use and it gives you more guarantees. It gives you ordering. If you go from begin to end, it's guaranteed to go in order because you give it a comparison function and it always stays sorted. And it gives you guaranteed order log n, insert and erase. Hash containers give you order constant time, guaranteed, insert and erase, which is really cool, but there are trade-offs. Things are in buckets, and so you may get a rehashing penalty from time to time. Some are better about doing incremental rehashing. And so be aware there are different performance characteristics. Maps are tree-based and give you guaranteed log n no matter what you do. Hash-based are sometimes somewhat faster because log n is almost constant for big N. Remember that. Log n is pretty much constant. And so hash can do a little bit better depending on the constant in front. But you might trade off this hashing penalty, and you also trade off ordering. You stick it in, and traversing from begin to end may go in some jumbled order that is based on the hash function, not on the values. But that's the code you write. And now in one screen we've said, oh, by the way, there's this dynamically resizable vector and this fixed length vector. Oh, and by the way, we have 2 kinds of associative containers, one hash-based, one tree-based, and it's simple code that fits on a slide. There's the summary of containers in STL. Now, I talked a bit about loops. Now, on the left-hand side, the old way is writing a for loop. And the left-hand side code is still perfectly valid. It still compiles. I would just encourage you to do it the right-hand way, because it's semantically the same and actually sometimes faster. And it's simpler. On the left-hand side, look at the for loop. We talked about this already. For auto I equals v begin, I doesn't equal vn plus plus I. You look up to for, and you don't know more than there's a loop. Whereas on the right-hand side with for each, you know exactly what's going to happen. And you can still write exactly the same loop body in the lambda. Exactly the same code, because lambdas can be arbitrarily sized. So you can pass the loop body to the algorithm, which is a very powerful thing to be able to do. Just sticking with the for to for each example, would you expect that the left-hand side or the right-hand side would be faster? Left. How many would say, yeah, I'd expect the left-hand side to be faster? After I'm doing it on my own. You tried it? It is faster? Well, I would like to see your code and try it again, because when I tried it, it's perfectly valid. You know, and this is the thing about performance measurements, right? Never believe someone when he says, and here's the performance that's true all the time. Oh, really? On what day of the week? And did you sacrifice a goat? Was it a full moon? And what compiler switch settings did you use, right? So both of us could be right. However, all I can say is when I've tried it, and even with a simpler example that compares going through for each with iterators and a lambda, compared to using a naked for loop with raw pointers with merely pointer plus plus and integer increments, which is like the baseline you don't get faster than, with /OX, full optimizations, the right-hand side was still faster, in part because as soon as you express your program at a higher level of abstraction, many STL implementations already partly unroll for eaches for you. You don't have to do it by hand. Also, that lambda is typically used to instantiate a template. It is here used to instantiate a template, and we're really good in C++ about inlining. All that abstraction you said, yeah, that's for you. We make that all go away at the compile time. That's what we do. It takes a couple of seconds longer, but we make it go away. That's our trick. So don't assume there is a performance penalty for writing the clean code on the right versus the less clean code on the left, the more manual code. You might find it's even faster on the right. So for the second example, notice my loop at the bottom left. Look at it real quick and tell me what it does. Right, exactly. So I gave you a couple of seconds, 5 seconds, and it wasn't enough. because you're parsing auto I, okay, but then why am I not initializing the I in the for statement? Oh, because I'm going to use it after. And I haven't even got to reading the rest of it yet. It's still fine, it works, we've written this code, there's nothing wrong with it. But today I can write auto I equals find if, begin v, end v, and put the condition as the predicate in the lambda I pass to find if. Find if as a standard std : algorithm. Begin v and end v is the new standard way that you should always, in your C++ code on any compiler, any platform, always use the new standard non-member versions of begin and end, because they'll work just fine for anything that has a .begin and a .end, and for anything that doesn't, including WinRT collections. I mentioned that yesterday. And I'm passing a lambda, which again is a standard thing. It's perfectly vanilla C++ 11 code, but arguably cleaner and easier to read and expresses my intent with find if much more naturally. So for, while, and do, prefer looking to standard algorithms and lambda functions. Use for each in particular as your bread and butter algorithm. Whenever you have a loop to visit each element, ask yourself, why am I not writing for each? And if you're looking for an element, ask yourself, why am I not calling find if? And there are also binary searches available as well. And prefer non-member begin and end. So by default, reach for each and find if. Now, if you do want to do, say, binary searching, not just visit every element in a sequential search, that's where you have the standard sort algorithm. And you have a bunch of binary searches, lower bound, upper bound, equal range to find the range of equal elements. There's about 4 or 5 of them, including binary search, which returns a bool. Who thought that was a good idea? Anyway, everybody makes a mistake now and then. Hey, if you're going to find that much out, can you tell me more? Anyway, enough. So sort, lower bound, et cetera, are your friend. It's usually sort and lower bound you'll use. Now you have to remember, use the same predicate. Don't sort with one predicate and then do binary search with another. You will not be happy. You might get the answer by luck. Use the same predicate. So how can we remember to use the same predicate? Oh, by the way, that part's easy. Remember all those rules we used to have if you've been doing C++ for here's how to write a predicate, inherit unary function, binary function, instantiate with the right templates, oh, provide these things, and make sure. Just forget all that. If you don't recognize that, ignore that last part. It's not true anymore. Use a lambda. Write my predicate as a lambda. That's how you write function objects these days. Autocomp equals, here's what I take, and here's what I return. I want to sort by weight. Great. And then I just take that variable, whose type I don't really ever need to know. It's a compiler-generated type anyway. And I just pass it to sort and pass it to lower bound, and I'm done. Clean, safe, exception safe, and fast code. When you're coming to C++ from another language, in particular, if you are used to managed languages, which are perfectly fine, again, they emphasize programmer productivity and make a lot of things easier. Well, you'll find that C++ has caught up on a lot of that by taking the features that weren't in conflict already anyway with performance and brought them in. But there's still some extra convenience, and you pay for it, but you get it. I mean, that's what you want, and so you should get that productivity. And you get automatic garbage collection, JITting, virtual machine under you. That's great. One thing to remember if you're coming from that world to the C++ mindset, even if you're in a managed language like C# or Java, you already have 2 kinds of types. You have reference types and value types. Reference types have virtual functions. They live out on the heap. You always heap allocate them with new. And value types are things like in C# structs, or in Java you can't really write your own, but you get the ones built in, the fundamental types like floats and so forth with all lowercase. Those aren't always heap allocated. They go where you put them. If you have one on the stack, it's on the stack. If you have one as a member of a class object, a reference object, it's a member of inside that object, right? So even in a managed world, you have reference types and value types. They're there. We already know about these 2. C++ has always had them too. You happen to say class to author both of them, but they've always been there too. The difference in the mindset is, in managed languages, reference types are the default and the vast, vast majority, and value types are things you reach for sometimes. In C++, classes are value types by default. But you can also write reference types, and many do. So it's just the default has changed. We default to value types, which tend to be more efficient, and you can put them where you want. You have control. So for example, on the left, we talk about copyable value types. Whenever I have a value type, like a C# struct or a C++ copyable class, the default, it's all about memory control, layout control. Things go where I put them when I leave them there, and they stay there. And I can express automatic lifetime by attaching their lifetimes to other things. Reference types get to be polymorphic. These are all about base classes, virtual functions, override control, interfaces, those kinds of things. Every language has them. It's just that one is the default or the other is the default in the different languages. Now, in C++, how do you author them? So on the left hand, copyable value types you get by default. You just write a class and you get the copy constructor and now the move constructor, copy and move assignment operators by default. I'll talk about move in a moment. To get a polymorphic type, which is the default in Java and C# class, you want it to be polymorphic, you have to do a couple of things. First of all, you have to turn off copying. That is easier than it used to be because you typically, at the top of your hierarchy, one guy inherits boost non-copyable, and you're done. This is the boost library, which many of you are probably familiar with. It's almost as good as in the standard. It's widely and freely available, and I know many of you already use it in your projects at work. So reach for boost non-copyable, or if you have to, just write a macro that writes the 4 functions yourself. It doesn't have to be obscure, difficult code. It can be just, hey, look, this is not copyable. I opt out of the default. And then I have virtual functions. And by the way, I can say virtual draw override. By the way, that compiles in Visual Studio 2010. I don't know if you knew that. But the standard only adopted that later. So fortunately, they adopted the same syntax we already shipped. So in the developer preview you have now, you can write this brand new C++11 code that was only invented 2 years after we wrote it in the compiler that you were having before. So if you use Visual Studio 2010, again, it works. And then the standard actually said this 2 years later. But you get a warning saying, warning, non-standard extension used. Just ignore the warning now. Hopefully, we should turn that off. It's not turned off in your developer preview, but it's not true. It's now standard, and we support that now. Now notice when I inherit circle from shape, I don't have to say non-copyable again. It's just inherited. Shape is also by default non-copyable. I don't have to remember all the time, oh man, did I remember to turn off the copy constructor this time? It's not this big gremlin. You just say non-copyable once at the top and you're done. And you get to say explicit override control. If I want to say, I intend this virtual function to be an override of a base and I misspelled it by calling it drew instead of draw, I will get a compile error that tells me, just like in the other modern languages. Now, that's talking about, in one slide, about reference types and value types, because the default is now value, and this is how you opt out to reference. But now, because value types are so good and offer you so much control, let's talk a bit more about how you deal with them these days. In C++11 and in Visual Studio 2010, move semantics, which, as I mentioned, we implemented already in the last release, and even though they've changed several major times in the standard, we've gone back and tracked it every time. So we now implement in Dev 11 in Visual C++ 11, VS11, I'll get the right acronym eventually. We implement the latest and standard version of move semantics. So it's been updated since the move semantics. And if you know the details, you'll notice that we did that C++11 language conformance work in this release. So that's in your developer preview. But what move semantics let you do is to say, if I have an object that's about to die anyway and I copy it, if it's an expensive object, I can just steal its guts. I don't actually ever need to do a deep copy. So the idea is C++ is all about value types because they give you great control. But it's true, sometimes you get temporaries because you make copies that you didn't need. Most of these evaporate now by just recompiling your code, which means by doing nothing, which is really cool. It has profound effects, such as, for example, how many of you in C++98 would ever have let this code pass code review? What's wrong with it? Exceptions, well, it's exception safe because it will clean up if there's an exception, but what's the performance problem? Copy. So if I copy the set of widgets, what's wrong with that? That's a set of 1,000,000 widgets. Why don't I just take that memory spike of having 2 versions of it once, only to throw one away, and then you'd never return these by value. So what people did instead is they returned by reference, or they took out parameters by pointers and references, or heap allocated, returned you a pointer to a heap allocated one. You don't need to do that. Don't think about that. That's just not necessary. Return it. It's a value. We move values automatically by default because return values we know are values. They're about to go out of scope. They can't be used again. It is perfectly safe to steal the guts of an object you know by construction is never going to be used again. It's an organ donor. I like that. What's your name? Javier. So anybody who says that, it is the Javier organ donor metaphor. So he's an organ donor. Thank you, Javier. We have such a... Okay, go ahead. Give him a round of applause. So now let me run with that metaphor. So we want to make sure we sign our cards. To get this, I'll show you on the next slide how you do it. Good, I like that. So notice we have no problem here with returning a set of widgets. Could be 1 billion elements, a trillion, a quadrillion. Well, now you're in 64-bit, but it can be as many as you want. And you know you're not going to do a deep copy when you return that by value, say in this case to assign to a widget. Now, there are still cases where if I want to use the storage that the recipient already has, I want to pass him in by reference and reuse his storage. But in many cases, I'm just as efficient just by simply returning by value. Now, if I have a vector of strings, I know those are contiguous. And remember, when you insert in the middle of a vector, what happens? Shuffle everybody over by one and make a space, which is copy, 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 and to make a space to stick somebody in the array. It's all safe because you expand the storage if necessary and so forth, but it requires all this copying. I should have said this before, so let me say it now. The way to think of move is it's an optimization of copy. All we did in C++11 was to say, hey, look, this is a value-based language. Value types are cool and useful and efficient. Let's optimize them even more. So we optimized copying. So if you insert in the middle of a vector of strings, there will be no allocation. There will be no reallocation of the strings. I mean, you need to grow the vector if it was already full, but you will not be reallocating any of the strings, even if you grow the storage of the vector itself. You're not going to be allocating more storage on the heap for Tom, Richard, or Harry. Tom, Richard, or Harry you will insert, but that's it. None of the existing ones will you duplicate. Now, it's still not free, right? I'm not trying to sell you a pig in a poke and say, look, it's all free, just marvelously do this. I'm just saying the large lion's share of the cost is gone. You still are stealing the guts, which for a string typically means a pointer assignment and a couple of integer assignments, which is a lot better than malloc. And finally, when you have even large data types, return by value applies to overloaded operators too. And a huge matrix is a typical example of that. So return by value, without the contortions of extra proxy objects that we used to go through, just work much better. Don't be afraid of value types. They have been optimized. Now, how do you sign your card to become an organ donor? The way you do it, now in some cases, in a few cases, the compiler can generate move for you automatically. The good news is, you remember how sometimes the compiler generates copy for you automatically when it shouldn't, and that's why we have the opt-out, non-copyable? When the C++ committee looked at adding move, it found that there were good reasons to enable move implicitly, but not as aggressively as copy, because we had lots of experience with copy, and the implicit copy operators and constructors were very useful, and those parts we kept, except when they weren't, and those parts we didn't keep for move. So sometimes they're implicitly generated, but you will find you need to opt in sometimes to say, hey, I'm movable, and it's safe to move me. And then you just simply write the operators like this. Instead of taking a const myClass reference, you take a non-const myClass rValue reference, that double ampersand, and then you steal the guts of the other object. Now, usually that's enough. Move means that once I've moved from an object, it is still a valid object of its type, but in an undefined state. Typically, the next thing you do is assign to it. And then you can use its value again. Otherwise, you don't know what its value is, because it's really empty. It's a hull waiting for a new state, but it's still a valid object of its type. If it's not valid to use this thing in this state, you may want to put a check in some methods to see if that's the case. And so I'm using that as an example here. If not data, you might throw an exception. Generally, you don't have to reach for that, but for completeness, here are the two things to write, and then optionally, you may want to check just to make move from object safe. At the bottom right, if you have copy, you usually want move unless it's like a point class with two integers, and you can't do better than just a shallow copy, just a copy of the two integers anyway. But for more expensive value types, maybe that own resources on the heap or something, definitely implement move. Just not if implement move basically if you can do better than a deep copy. And often you can. If you can't, don't worry about it. If you have move, it doesn't mean you want copy, by the way, because now there's this new category of types, move-only types, that are not copyable, like unique pointer. I better not be able to copy that, because then if I can't, I might have two unique pointers that point to the same object. Ain't so unique no more. That's what shared pointer is for. So unique pointer is not copyable, but you saw me, wait a minute, but you saw me have vectors of unique pointers. How is that possible when vectors have to copy things down when you insert? Oh, they move things down when you insert. Okay, so it all works. Somebody was paying attention when they upgraded STL. So we have move semantics in the language. STL is fully move aware. Vector of unique pointer, move only type, can't copy it? No problem. Don't try this trick with auto pointer. It's deprecated. For those of you, auto pointer was the unique pointer before there was move semantics, and it tried to kludge it. It shows why you need move semantics. It's no longer part of our universe. It has disappeared. That's not the pointer you're looking for. Finally, let's talk about when I want to go outside of C++. So far I've tried to show you, in just a very few elements, there's a very happy path through C++. It is very clean, safe, and fast by default. Exception safe, doesn't need garbage collection, automatic memory management, and the code is pretty much line for line what you'd write in any other modern language, OO language. What happens on ABI boundaries when you want to talk to other C++ modules or other modules that may or may not be implemented in C++? There are three steps to think about. You probably know the first two already. One step is, and this is useful even not on module boundaries, for really popular types, use the Pimple idiom, which you'll see we use a for declared pointer in the outer class, say my class, and then all of its private methods too, and data go into the separate class, which is defined only in the CPP file. So the header file above the line simply mentions, by the way, there's a class of this name, but all the private guts are gone. And other clients only see the header file. Other C++ clients only see the header file. Therefore, if you change the private implementation, all you do is compile the one myclass CPP file and just relink. You do not have a compile cascade, you relink. So this is very useful for a compiler firewall. Sometimes people complain that C++ exposes implementation. Even if you just add a private member, you have to recompile everybody who uses it transitively. For those kinds of types where that matters, use the Pimple idiom. It's already well known and popular, but here's the C++11 twist. What's the pointer type you use to hold your impl object? It used to be, the answer used to be, well, a raw pointer, but remember to copy and delete in all the right places, or an auto pointer, but that's not really quite right because it's kind of goofy. And so remember to turn off some unwanted behavior. And the real answer is use a unique pointer. Same one we were already talking about. I uniquely own my implementation. It just naturally follows. Now it's nothing new from our previous rules. And I don't have to teach any extra rules. It just works. Now, that's if you want to talk to other C++ types through a compiler firewall without committing to their implementations, and also just to avoid rebuild cascades. But what if I want to talk to non-C types? Well, C is the lingua franca of the world. Every language pretty much understands and can bind to C, every operating system. And so the answer up until today has been implement a flat C interface. Here's how you do it. So I have an object, class widget. It's got constructors, destructors, methods. How could I possibly teach C about that? Right? OK. Let's jeer. How could we possibly teach C about that? Boo. OK, it's not going to work. I'm not going to ask for a show of hands people who love C because I'd have to put mine up. I like it too. It's very useful sometimes. But when I don't have a C++ compiler. So the way you project it, though, but seriously again, the way you project it in C, which lots of other languages can understand, is it's in a way that is not foreign to C. Objects are not foreign to C. This whole thing where I got us to boo or tried to, it's actually never been true. Look at the C standard library. fopen is a constructor. Of course it is. It takes some parameters and gives you a file star. That's a this pointer. You just carry around your this pointer. It's really a this pointer. You have a destructor. It's called fclose. What does fclose do? It takes your this pointer, your file star, and returns void. That's a destructor. Does a file have member functions? In C? Sure. fseek, ftell, what do they take? Explicit this pointers. You pass in the file star. So that's how you flatten a C++ class to a C API that deals only in fundamental types. So we only deal in C built-in types, including pointers and structs thereof, because we have a forward-declared struct widget. We don't say what its size is. And then the constructor becomes a widget create function that takes whatever parameters and returns a new widget, star. And remember, widget star is a forward-declared type. It's type safe, but nobody knows what the details of the type are. My destructor becomes a destroy function, which takes a widget star and then nukes it. And then my method takes an explicit this parameter. So all of this flattens, and I just write extern C. I nail down the calling convention. Now any language can understand this. This is the tried and true way to project, to flatten the C++ API. And you can do similar things for templates by pre-instantiating them for certain combinations of types. And this is the one extra slide. Today, as of VS11 on Windows 8, you now have a third option. On Windows, we're now for one slide not talking about portable C++. This does not work on other platforms. It works on our compilers today. You can also project types that are WinRT types. Use the stuff we talked about at the rest of the conference, at my last talk. Ref classes, value classes, and now any language, now you can express an OO interface, rich, class-based API that any language on Windows can understand. And here's the difference. On the left-hand side, you have how you write typical OO code, author it, consume it in standard C++. I have a class point. I say drawable, that's a value type. I say drawable is non-copyable because it's a base class. I have shape and circle implement drawable, and the circle implements shape. And then I use them with make shared, and I have a shared pointer to drawable. All the stuff we just talked about. On the right-hand side, I simply declare my intent. I can have a value class point. That is projected through WinRT as an efficient value class, copyable. I can have an interface, iDrawable, and that virtual was optional. I could have just said void draw. Public is optional. Abstract is optional. I have a ref class shape, implements iDrawable. Ref class circle implements shape, inherits from shape. Yes, you can do inheritance of WinRT classes. And then I just use them with ref new and hat. And as a consumer, that's all I need to know. Clean code either way. Native portable C++, WinRT C++, and they're very similar. And they're fully integrated. You can use them together, and they're clean. I may have said this before. They're safe. They're fast. The types that you declare here are ABI safe and cross-language. I can say the kind of type that I'm interested in, and all I have to learn to consume all of this, and anything else I get from other languages is hat and ref new. So we've talked about where we've come from, that modern C++ code, native and managed, is nice, clean, safe, and fast, what you do on the boundary. And just in summary, we were really seeing across the industry and also at Microsoft an increased interest in C++. So you've seen that we're renewing our commitment to provide a new programming model for Windows 8, to give C++ first-class access to all this cool new tablet and mobile kind of application, to get the full power of your CPU and your GPU with C++ AMP and other technologies that we're putting into this product that is working on the tablets that you got this week, to use the hardware capabilities of Windows 8 to their fullest, because we're the to-the-metal power and performance language, and to build for ARM, which Visual C++ has never done before. So that's what Visual C++ is, the power and performance tool for Windows. If you want to find out more, some of these sessions have already happened, some will happen in the future, but for those of you watching and also those in the room, for those who've happened before, they're all going to be on demand. So they're already either on demand or will be. Especially take a look at using the Windows runtime from C++, all the Metro style app stuff, but also GPU computation. And on Channel 9, there's additional talks beyond what you're going to see live here at Build, talking about many of these cool topics, including the Renaissance, Metro-style apps, under the covers, what happens. And there's a lot of goodness there for you. All of it is available from C++, clean, safe, and fast. And I think that if you give it a try, you'll really, really enjoy it. I hope you do. Thanks for coming, and I hope you enjoy the rest of the conference.